everybody, anything everybody says is recorded forever.
Yeah. Live.
Okay. YouTube. No. Access பண்ண முடியும். But you have to ask them whether I mean, you don't open. Okay. That is an restriction. This is also means same program is like you know. Ask okay. Just ask because they have to W274. I just wanted to see the participants that
Good afternoon, sir.
You can try to, but they have to give up. That's it. But
We last ID to
that will open with standard consider. That also one problem there, and what to be access.
Good evening, Dr. Kamachi.
Good evening,
Good
sir.
evening, good evening. Good evening. Good evening to all.
Sir, good evening, sir.
Good evening. Good evening, Rajan, Kamaraj,
Good evening,
Indian.
sir.
Yeah. Good evening, sir.
Good evening.
Professor Surya Khalid is also there.
Yeah. Good evening, Divakar, Karthik, Albert, I think Ranijat.
Yeah, good evening to all of you.
Good
Good
evening,
evening.
sir.
Good evening.
Yeah.
Anything?
Professor Murugan, I think we can start.
Hello.
Shall we start?
Professor has to join. Professor Jagdish Kumar. Professor Jagdish Kumar?
Yes, sir. I am here. Start, sir.
Okay, sir. Okay. Rani madam?
A very good evening to one and all. During this pandemic period, the moment is sufficient for all of us to gather together online for Dr. Placid Memorial Lecture Series. I request Dr. Sundararajan, Chairman, IIM Chennai Chapter, Beats India Limited, to welcome PRML 2020 speaker, other dignitaries, and the online participants.
for this 12th Dr. Placid Rodriguez Memorial Lecture over the online medium. First and foremost, I would like to welcome Dr. Surya Kalidindi, and he is a very famous professor from Georgia Institute of Technology from USA. And he holds a Regent Professor and Ray and Frank Neely Chair. Also, he holds as the Interim Director of Novelis Innovation Hub. I had an opportunity earlier to listen him in a different forum, and where Dr. Surya has presented an excellent overview on how the data science can be exploited into the material science. And that was a very state-of-art research he is doing at his laboratory. And welcome you, sir, for this 12th PRM lecture. And I would like to invite the chief guest of this event, Dr. Jagdish Kumar, Dean Academic Courses from Indian Institute of Technology, Madras. Also, it's my immense pleasure to welcome Dr. Kamash Mudali. He was a PRML speaker earlier also, and very close associate of Dr. Placid Rodriguez. And thank you, sir, for being here. And it's my privilege to also welcome the fellow organizers like Dr. Shaju Albert, Dr. Ronnie George, Dr. Karthik, and Dr. Devadar from IGCAR. Also, Professor Kamaraj, and as well as Dr. Murugayan from IIT Madras, Dr. Srinivasa Rao Bachi, for all of you put and a lot of efforts over here to organize this event in an online medium. And it's also my immense pleasure to have a welcome address of Dr. Placid Rodriguez. He was a director then when I was a student at Indira Gandhi Center for Atomic Research. Yeah, I feel honored for being here to welcome you all. And with this, I will hand over to the proceedings to the Dr. Ronnie George. Thank you.
Thank you, sir. Now I request Professor M. Kamaraj, IIT Madras, Chennai, one of the founder members of the internal committee, to explain the genesis of Dr. Placid Rodriguez Memorial Lecture Series.
Okay. Thank you, madam. I joined Dr. Sundararajan to welcome you all for this program, PRML program, and I'm very happy to say a few words on Dr. Placid Rodriguez lecture. To perpetuate the strong scientific spirit and the value system which Dr. Rodriguez practiced during his lifetime, Dr. Placid Rodriguez Memorial Lecture was instituted by the Indian Institute of Metals in 2009 under the pioneering leadership of late Dr. Baldev Raj. Since then, this event is being organized annually by the Kalpakkam and Chennai chapters of the IIM. Also, I am very happy to share previous speakers delivered in the Dr. Placid Rodriguez Memorial Lectures. In 2009, Professor Atul Chokshi, Indian Institute of Science, Bangalore, he delivered a lecture, followed by Professor Sriram Ramakrishna, National University of Singapore in 2010. And in 2011, Dr. Srikanth, former director of NML Jamshedpur, and Professor Murthy, D.S. Murthy, IIT, currently IIT, director of IIT Hyderabad in 2012. In 2013, Professor Indranil Manna, former director of IIT Kanpur, and current IIM president, Dr. Amul Pogale, earlier was a former director of DMR Hyderabad. In 2014, he has delivered this lecture. And Dr. G.K. Dey, Associate Director, Materials Group, DRC Mumbai in 2015. And current Director of IGCAR Kalpakkam, Dr. A.K. Badri, delivered this lecture in 2016. And Dr. U. Kamachi Mudali, Chairman and Chief Executive of Heavy Water Board in Mumbai 2017, followed by Dr. Samir Kamath, Director General, Naval Systems and Materials, DRDO 2018. And last year, Sri S. Somnath, Director of BSSC ISRO Trivandrum. Dr. Rodrigues, born in Quillan, Kerala on 5th October 1940, obtained his BSc from Kerala University, BE Metallurgy from Indian Institute of Science, Bangalore, and MS from University of Tennessee, and followed by PhD from Indian Institute of Science and MBA from Indira Gandhi National Open University. He joined the Department of Atomic Energy in 1960 and moved to the Indira Gandhi Center for Atomic Research, then known as a Reactor Research Center, in 1974. He established one of the leading metallurgical research laboratory at Kalpakkam. He was director of IGCAR Kalpakkam from 1992 to 2000. Subsequently, he served as the chairman, Recruitment and Assessment Center of DRDO Delhi and Raja Ramana Fellow and AICT INEA Distinguished Visiting Professor at IIT Madras. Dr. Placid Rodrigues had an exemplary career of 4 decades leading research in metallurgy, materials development for fast reactor program of our country, shaping of human resources in defense program and academic institutions. Dr. Placid Rodrigues has been a member of editorial board of several reputed international journals in metallurgy and material science, and also was the chief editor of transactions of the Indian Institute of Metals. Dr. Rodrigues served as the president of many leading professional societies and also is a recipient of many national and international awards. He has been a fellow of many prestigious academics of our country. Dr. Rodrigues passed away in Chennai on 31st August 2018. So with these few remarks, I welcome you all once again for this 12th Dr. Placid Rodrigues Memorial Lecture. Thank you.
Thank you, Professor, for the excellent Dr. V. Jagdish Kumar, Dean, Academic Courses, IIT Madras, Chennai, Chief Guest of the function to address the gathering.
Good evening and welcome to the 12th Dr. Placid Rodrigues Memorial Lecture. I am really honored and glad to be part of this function. I was also part of the last year's function for the first time. I came across this particular lecture series. In fact, at the time I shared my interaction with Professor Rodrigues. Good things can be repeated, so I'm going to repeat them, not in the same manner. I met Professor Rodrigues as a research student. I was doing PhD at IIT Madras, and that was the time the FBTR at Kalpakkam was being built. So I was being an instrumentation person. I was actually helping quite a lot of research students in IIT Madras. One such research student was one Dr. Venkatesan, who was doing PhD in metallurgy, and he was working in IGCAR Kalpakkam. Then also I met Professor Venugopal, who is now director of NIT Nagaland, right? To both of them, I have done instrumentation help, building instrument for measuring things in their experiment. And so when I heard that the FBTR is going to become critical, I wanted to actually visit. So I went to Kalpakkam, met Professor Rodrigues. He was the chief at the time. And I don't know, at the time, being a research scholar at IIT Madras, I always thought that I'm great, I can do anything I want. So I just walked into his office and introduced myself and told him, I want to see this before it becomes critical. I want to go inside and see. Then he smiled at me and said, young man, you can go in, but you cannot come out, because everything is secret. So once you see it, you cannot come out and tell the world. So I was really struck off, and after a few minutes, I said, "It's okay, sir. It's not a problem. I'll go." Then I don't know what made him rethink. He said, "No, no, no, wait. I will take you around." So he actually gave me a personal tour of FBTR before it became critical. So I am ever thankful to him. Afterwards, whenever he used to come to IIT, I used to meet him either in the main guest house or in the department, and talk to him about, in general, about science and especially about atomic energy. So maybe others know Professor Rodrigues as an excellent researcher, an achiever, a great human being, but I know him actually as a humanist. He thought the I am fairly certain he looked at my face and saw the disappointment that I am not going to see the FBTR, and changed his decision and shown me around. So it once again gives me great pleasure to be part of this lecture series, and I am sure that all of us are waiting to hear Professor Surya Kaladindi lecture. So I would not stand between you and the great person. Sir, thank you for accepting to deliver the lecture. That's it from me. Thank you very much.
Thank you, Professor. Now I request Shaji P. Albert, Chairman, PRML Committee, Director, MMG, IGCR Kalpakkam, to address the gathering.
Good evening, everybody, and it gives me great satisfaction to be with you all for this lecture series. So I welcome personally Madam Blossom Rodrigues and Menaga Rodrigues, and maybe many other people, maybe the Sudarshan Rodrigues, for this event, and also welcome my friend Sundarajan, my colleague, the friend Kamaraj, and Divagar, and also our chief guest Surya Kalidindi for this lecture series. And as we know, many of you closely known to Rodrigues, they will agree with me, as Dr. Jagdish Kumar told. We are remembering him and honoring him, not only because he was a great scientist, but also because he was a great human being and he was a great mentor. And another important thing about him is he was an institution builder. I think, as I told last year, actually, Placid Rodrigues derived his name from the name Placid comes from the feast day of the saint on his birthday on October 5th. Is celebrated as a feast day of Saint Placid, and Saint Placid was a monk, but he was an institution builder who built many monasteries in the place where he lived. And you find this is precisely what Dr. Rodrigues did. He was a metallurgist, he was a scientist, and he built an institution, the Indian Institute of Metals, Kalpakkam chapter, and IGCAR, and the metallurgy program in Kalpakkam. So all the institution which he built and nurtured. And not only he built the institution, he also nurtured many scientists. And I think myself and our director, Dr. Bhaduri, maybe the last two of the scientists whom he guided for their PhD. Many of them are retired, and even one of them is Dr. Kamachi Mudri is already there in the audience, and who just retired a few months ago. So that not only the generation of Rodrigues is passing away, but even the next generation. But still, we remember all the people and the metallurgy community in Kalpakkam remember him for his the human approach. And he has another good character he was having is he remembered everybody. And even after several years, he could even call anybody whom he has interacted with by their first name and ask them about their what they are doing, how they are, and about their personal life as well as their professional life. He was such a great human being. And I have a special happiness to be in this lecture, because this lecture topic is what is talk about. Professor Karandini is going to talk about is about deformation, a topic which was very close to Dr. Roddick's heart, and in which he has made a significant contribution in the science of deformation of materials. And I also, this today's lecture, in addition to being online, it's a special thing because it is after several years we are having an academician speaking on this lecture, because for several last from 2014 onwards we had a scientist and scientific holding responsible position in various scientific institutions have been giving. But today we are back to the academician, and I am sure it will be enriching to many. And I welcome Dr. Surya Kaladindi for this lecture, and I am sure he will be honored, and the audience will be honored by this lecture. Thank you so much.
Thank you, sir. Let me now request Dr. Divakar R, Chairman, IM Kalpakkam Chapter and Associate Director, MEG, MMG, IGCR Kalpakkam, to introduce our PRML 2020 speaker.
A warm welcome to all. It is an honor to introduce this year's Placid Rodrigues Memorial Lecturer, Professor Surya Kaladindi, Regents Professor, Ray and Frank Levy Chair Professor in the George Woodruff School of Mechanical Engineering, with joint appointments at School of Computational Science and Engineering and the School of Material Science and Engineering at Georgia Institute of Technology, USA. He is also serving as the interim director for the newly established Novelis Innovation Hub at Georgia Tech. Dr. Kalidindi's research interests are broadly centered on designing materials for optimal performance in any selected application and identifying hybrid processing routes for its manufacture. As his joint departmental affiliations indicate, he has employed a harmonious blend of experimental, theoretical, and numerical approaches in his research to make seminal of crystal plasticity, microstructure design, and materials informatics, some of which we will look forward to being covered in today's lecture. Professor Kalidindi is delivering this lecture today through his alma mater, having earned a BTech in Civil Engineering from the Indian Institute of Technology, Madras. He then went on to the US to earn an MS degree in Civil Engineering from Case Western Reserve University and a doctorate in Mechanical Engineering from the Massachusetts Institute of Technology in the USA. Dr. Kalidindi took a faculty position with the Department of Material Science and Engineering at Drexel University as an assistant professor, where he subsequently served as the department head during 2000 to 2008. Under his leadership, the department experienced a tremendous growth and was ranked 10th in the US among material science and engineering programs in 2006. During 2009 to 11, Dr. Kalidindi served as the department head for mechanical engineering at Drexel University and has been at Georgia in his current position since 2013. Dr. Kalidindi has been elected a fellow of the American Society of Metals International, TMS, and ASME. In 2016, he and his group members have been awarded top prizes in the National Material Science and Engineering Data Challenge, sponsored by the Air Force Research Lab in partnership with National Institute of Standards and Technology and the US National Science Foundation. He has been awarded the Alexander von Humboldt Research Award, the Vannevar Bush Faculty Fellow, and the Khan International Award. He is also recognized by the Government of India through the Visiting Advanced Joint Research Faculty Award, also known as Vajra Award, which is instituted to bring a strong international connect to the R&D ecosystem of India. Professor Kalidindi has authored 2 books, 2 edited volumes, 8 chapters, and over 250 research articles in archival journals. His work currently enjoys a H index of 77. He has advised over 90 graduate students and many undergraduate students in research. With this brief introduction, I invite Dr. Kali Reddy to deliver the Dr. Placid Project's memorial lecture. And may I also request the audience on WebEx platform to keep microphones on mute and make use of the chat facility to record their questions, comments, which will be taken up during the interactions at the end of the lecture. I hand over the mic to Professor Kali Reddy.
Okay, so can you guys hear me?
Yes, sir, we can hear you.
Okay, so let me just move this thing out so that okay. First of all, let me start by thanking all the organizers for this wonderful honor. It really is I'm really deeply humbled by this recognition, and especially even before today, I have been looking at Dr. Placid Rodriguez's accomplishments, and it really is incredible. As many people said, he is not just an incredible scientist, but also an incredible human being. That really deeply humbles me, and that I'm being asked to give this lecture. In terms of topics of what I'm going to talk about, because I did a lot of work in deformation and crystal plasticity, but I thought after being inspired by Dr. Placid Rodriguez in the variety of things he has done in his career, I thought I'll give a much broader talk and actually give you a little bit more futuristic talk than the past, because he was always from what I understand and what I learned, what I read about him, he was a real visionary. And I'm trying to move my okay. Yeah, he was a real visionary, and I'm really impressed by the kind of things he got interested in and the broad variety of things he got interested in. And for example, as several people already said, and I think everybody knows about his work in individual dislocations and trying to understand how they contribute to continuum dislocations or groups of dislocations, and how they actually affect deformation, ductility, and strength in metals and highly deformed materials. Obviously, given his position, he was also very interested in radiation damage caused by radiation swelling, especially in nuclear materials. And he always argued for basic and fundamental experiments. I hope I'll expose some of those basic and fundamental experiments that are now possible, but we shall see. Then that was just on the dislocation side, and that's metal side. But beyond that, he was very interested in. I read some of his reviews and statements about his interest in application of dislocation science to problems in geophysics. Things like the earth mantles moving around, causing earthquakes and things like that. So that's incredible, from all the way from nuclear metals to geophysics. And then he got interested, and as if that was not enough, he got interested in quasi-crystals, amorphous solids, and line singularities, and then quantum phenomena. And again, keep in mind that he was doing this about a couple of decades back. Of course, these are now hot areas, but it's actually incredible that he had the vision to see that these are the areas that are going to be very important. And then he was also very interested in design of composites, things like mechanisms. He was always interested in physics-based explanations of how things are happening, and it looks like he particularly homed in on the importance of load transfer, fiber matrix load transfer, and microscale mechanisms of these phenomena. So with this, I'm really I want to appreciate this opportunity, appreciate this honor. This is deeply humbling to me, and I feel lucky, and I'm greatly inspired by his legacy. So now let me transition to what I'm going to talk about today. The main thought that I want to bring to your attention is this idea of how this vision of how materials innovation is going to happen in the near future. We are not that far away from what I'm going to try and explain. I think there have been incredible progresses in the last 10 years or so that actually make what I'm going to say very feasible, and it's something that you're going to see this generation of scientists is going to see very soon in about next 5 to 10 years. And this idea is that, of course, I mean, for a couple of decades, for more than a couple of decades, we have been doing in material science, we have been doing, let me switch this to a laser pointer so you can see. So for a few decades, we've been looking at materials phenomena at different length scales, material length scales, all the way from molecular structures or atomic structures to defects as dislocation scales and so on and so forth, all the way to mesoscale. And then, of course, the goal, the end user or the goal for all of these materials, the need to understand all these materials has always been that there is an end user in design and manufacturing who needed certain performance or properties or performance characteristics of materials. But the process of connecting all this, the information across these different length scales has always been extremely slow and extremely expensive. So typically, the numbers that are typically given is that the process of introducing a new material in a commercial application takes about 15 to 25 years. And of course, in the depending on the industry, it's at the high end of it. So aerospace and some of the highly regulated industries, it's close to the 25 years mark. So the process, so in material science, we understand enough at the different length scales, but essentially this process of collecting all this information, aggregating it, and presenting it in a way that the design and manufacturing people or end users are able to utilize and exploit this information is extremely slow. Now the opportunity is, how do you make it faster, or what can we do to change that? The opportunity is that there are these emerging data science and machine learning advances that have happened in the last 10, 15 years that look particularly appealing. And one of the good things they do is they automatically recognize that the data that you are collecting is uncertain, incomplete, and disparate. Disparate meaning that it may not really connect to each other. They may look very fragmented from each other. They come from very different sources because some of the data comes from simulations. For example, physics-based simulations of different kinds. There are physics-based simulations at the DFT using DFT theories or dislocation dynamics, phase field, finite elements, so on and so forth. Or they can come from very sophisticated experiments. But in general, we have few data points. We generally don't have the luxury of a very large amount of data, and we have bits and pieces of information that are inherently and fundamentally incomplete, uncertain, and disparate. But the modern machine learning platforms are actually designed to be able to aggregate that information and still be able to provide an answer across this interface if they are properly used. So that's what I'm going to talk about. I'm going to talk about a framework we have been developing, and we believe that it is time to establish these knowledge systems. So what we are calling as knowledge systems are process structure property linkages, but they're defined and organized at different length scales in such a way that the knowledge systems are interoperable. So that means that information goes from one knowledge system to another, and essentially they are interoperable. The advantage of this vision, if it is implemented properly, is that when there is a question from this side, from the design and manufacturing side, Because these are pre-computed knowledge bases, the knowledge bases are already in the computer, you're giving them an instant answer. You're not saying, you know what, guess, just wait. I need to do a few experiments and simulations. I'll get back to you in 3 to 6 months, which is currently what currently happens. You can actually give them an instant answer. But of course, because we would have so much uncertainty, the answer has to be accompanied or associated with some measure of uncertainty. Because if you just give an answer and don't tell the end user how sure you are, it's pretty useless. But on the other hand, if you give them an instant answer based on what you already know, and you say, you know, I'm only sure about this, 20% sure about it, or 89% sure about it, then the design and manufacturing people can actually take advantage of that and do whatever they need to do. The second advantage of a vision like this is that you give them answer instantly, but you recognize what the needs are, and then you can actually reprioritize or reorganize your activities such a way that if they actually come back with the same question again in a day or 2 days or a week later or a month later, you're hoping that you can actually give a better answer now that you know. And that's basically how Google search engine works. It is continuously learning based on the queries, and once you have the queries, then you actually reprioritize your internal knowledge systems, the way you're accumulating these knowledge systems. In some sense, it decouples the activities. So we are constantly in material science and engineering, we could constantly be building these knowledge systems continuously 24/7, and then at the same time simultaneously give answers, instant answers to the questions that come up. So that's a vision. Now, some more details of how that can be implemented. So the one detail is that we have to define PSP linkages at different length scales. Again, in material science and engineering, process structure property has been used forever, pretty much since the birth of the field. Only difference is that I'm extending it to different length scales. So I'm actually, for example, as a specific example, I'm saying at a molecular scale, the placement of the positions of the atomic species or chemical species is a process variable. So if I define that as a process variable, electron density field would be a corresponding structure variable. And then the properties, for example, just as an example, is bond energy. So these lists are not supposed to be comprehensive. This is just to give you the ideas of what am I thinking of when I show the picture before. Now, if one can organize this, and you could argue that, yes, I mean, if our community gets together, we should be able to organize this. It shouldn't be that complicated. The main issues are that I think we'll settle very fast on definitions or mathematical definitions on process and property, because for the most part, they're very well defined. What we're not going to settle on is the definition, the quantitative definition of structure. Exactly what do you mean by microstructure? What do you mean by interface atomic structure? How do you quantify that? Not a qualitative definition, but a quantitative definition. And that's where we're going to struggle. And very soon we'll realize that most of the structure definition is high dimensional. That means if I really want to define an electron density field accurately, I need a very large number of, I basically need a field, a 3-dimensional field. And that's going to be very high. The number of parameters I need to specify is very large. So that's basically high dimensional. For it to be practical and to be able to do what I showed on the previous slide, we have to find a way to get low dimensional representations, practically useful representations, which basically translates to minimum information loss is maximum recoverability. In other words, we are going to give up some information, but we hope that what we give up is very small, but on the other hand, we get more usability. And the second part of it is that whatever we come up with has to be broadly applicable to different materials classes. And so there has to be some standardization. So if I keep redefining these terms for every material and I have to come up with another definition again next time, then we really don't have this interoperability I talked about. So those are the challenges. Now, I have only one slide of the underlying math. It gets very complicated, so I'm not going to do too much of the underlying math. There are papers you can read if you're interested in this. But the the way we are going to build these PSP linkages, which recognizes the uncertainty, but it also recognizes the fact that we have little data. We have small data, as opposed to, say, the driverless cars, for example. The people who are designing driverless cars systems, they have incredible amount of data. So we can't use the tools that they use. We need a different set of tools. So given those criteria, it turns out the Bayesian learning, Bayesian frameworks, or Bayesian statistical learning is just an advanced version of statistics. That's all it is actually quite appropriate for what we want to do. And the second question that we have to deal with is, what exactly are we going to learn using machine learning? So machine learning says you're trying to learn something, but exactly how do you define what is it that you're trying to learn? So the argument that I'm making in this paper and in this equation is that what we really want to understand, or what we want to really learn, is a governing physics in the phenomena, whether it is deformation mechanisms like Dr. Placid Rodriguez was interested in, or whether it is some other part, all the other things that we are interested in. We want to understand, we want to be able to, for a given sample you give me, I want to know what is the governing physics in that sample. So if I pose the question that way and then ask for help from machine learning or Bayesian learning, Bayesian learning says, well, if you are looking for something, it's pretty simple. This is what is called as a Bayesian update, and it has only 3 parts. And the first part is a prior. So it says, okay, take your best initial guess. So this represents what you think is your initial guess of the governing physics. And that requires a representation. So all of these could be very high dimensional. So none of these are simple representations. So imagine that these are vectors and arrays. All the variables here are vectors and arrays. Okay, so this is governing physics. And then a Bayesian update says, if you have a guess of anything that you're trying to find, the next thing you want to compute is what is called as a likelihood function. You're saying that I took a guess, but then I have this experimental observation. There are some observations I can make, or I have made. And now you're asking, so the overall Bayesian update is, since I made these observations, I want to know what is the posterior. So this is a prior, this is your initial guess. What is the posterior on the governing physics? But to be able to compute the posterior, you have to compute what is called as likelihood function. So basically this function says, for the given observations, what is the likelihood that you could have made those observations, right? What is the chance that set of observations could have been made? So again, in many other fields, not so much in material science, but in many other fields, this kind of Bayesian update has been used extensively. So this is not new for many other fields. But when you ask ourselves, how would we do that in material science, in the material science field? The complication is that to compute this term, you have to specify the physics. So it is saying, tell me the likelihood of, I need to compute the likelihood of these observations for a prescribed physics. Now, if you think about it, how do you do that? You cannot do it through experiments, right? Because you cannot control the physics. You cannot control the mechanisms. They are what they are. And sometimes we don't even know what they are. So the only way to compute the likelihood function is through physics-based models, like your DFT computations, or phase field computations, or any of those computations. What you're really doing is you're specifying the physics, and you're asking, okay, if I assume that the physics is this, what is going to happen? And that's called a likelihood function. And essentially, so the only avenue we have to compute the likelihood function is to use physics-based models. But if you brute force use physics-based models and try to compute the likelihood function, this is going to take forever, because as you know, all these computational tools are very expensive, take a lot of time. And this is where machine learning comes in. And machine learning has ways to produce surrogate models or reduced order models, even with small data sets, particularly the GP models and things like that. So they can actually produce these models. And if we have these reduced order models, then you can compute this likelihood function incredibly fast, very cheap. It becomes something that is impossible to do to something that you can do on just a regular desktop. You don't need anything more than that. And so it becomes incredibly cheap to compute that. But now you know it's a reduced order model. So you took on some uncertainty, a little bit of uncertainty. Now that if you follow this path and you're going to do this, and I'll show you examples as we go along, then you can do the update. Now you can ask the second question. Now you can say, well, if I can actually implement this, can I actually be smart about what experiments I do? In other words, now actually I want to optimize on how I select the experiments, because not all experiments carry equal value to me. So I want to be able to decide on which experiment is likely to be most useful to me. And that concept is called information gain. So basically, it's a definition of what is the change between the prior and the posterior. So the bigger the difference between the prior and posterior, the bigger is the information gain. So there is an entire set of tools that can be used to use information gain to give guidance on what experiment needs to be done next. So now, if you have these two elements together, then you can actually run this cycle in automated, and actually not even just automated, you can do it in autonomous cycles. So if everything is automated, you can actually create a lab where this is happening 24/7, and we are constantly evaluating materials phenomena and trying to understand materials phenomena very, very efficiently. Not only just, so it's a high throughput way of exploring materials physics and materials phenomena. So that's the overall vision we have, and that's what my group does, and we are interested in exploring this. And I'll show you, for the rest of the talk, I'll show you some details and some examples. The way I'm going to do this is I'm going to talk, for half of the time, I'm going to talk about this box, and the other half, I'm going to talk about this. And this integration, this autonomous integration, is just beginning to happen. So I only have a last slide or two in there. So it's not a lot yet. Okay, so, but that's the game plan. So I'll talk about this a little bit now, next. So in this box, the biggest issue in this box, as I said before, is quantification of structure. So this part is a process structure relationship. So given a process, what is the structure? And then given a structure, what is the property? So to establish these models or functions, we need a quantification of structure. So for this, we use this formalism of endpoint spatial correlations. Spatial correlations are like autocorrelations and cross correlations. So if you take this image and do an autocorrelation of this image, you'll get this. So the autocorrelation is called as a 2-point correlation, because it turns out that you can interpret that as a 2-point correlation. So the 2 points of interest are the 2 points separated by the vector. So the tail of the vector and the head of the vector. And essentially, that's called a 2-point correlation. So the raw image is black and white. Every voxel in this particular simple example is either white or black. And the pattern that you're seeing here is called a 2-point correlation. And it actually tells me something about the patterns that I see here. So it actually is telling me, for example, is telling me that the most common pattern here is actually this cross. Right? And again, you have to keep in mind that this is periodic, and if you start looking at it carefully, you'll actually agree that, yeah, that's the most common pattern. But there is more than 2-point statistics. There are a lot more things that can be computed. But essentially, this formalism is actually a way of quantifying the local neighborhoods you're likely to see. When you randomly pick a point in the microstructure and you ask, what does my neighborhood look like? Then it gives me a statistical description of that neighborhood. Okay, and mathematically it looks like that. What we have done over the last 10-15 years is to produce computer codes that actually efficiently compute this, and they're based on FFT algorithms, fast Fourier transform algorithms. So you can actually apply this to very large data sets. This is just a toy example, just to get the idea across. And also, most of the data sets I'll show you have more than 2 states. So this is what we would call as a 2-state microstructure, because I'm only allowing 2 states. In each voxel is either white or black. But then polycrystal microstructures and all kinds of microstructures, the theory is very easily extendable to as many states as you like. There's no big cost to it. it basically scales linearly with the number of states, essentially. So that's the framework. The one other detail is from a machine learning terminology, what we say is this is raw data. These are features. These are things that we are engineering some features out of it. And the number of features we engineer here is very large. So usually you can't use them as it is. So the number of features here typically is larger than the number of voxels here. So this actually is going the opposite direction of what I want to do. So to be able to actually practically use it, I take all those features and do a PC, a principal component analysis. And the principal component analysis is another orthogonal or Fourier representation, but in a discrete sense, because these are vectors essentially. So now I take all my features, put it into a vector, and then I can find the basis, and then I can find scores, PC scores. So it's pretty much like representing complicated functions in terms of sines and cosines and the weights of sines and cosines. Turns out for most microstructures, the real feature vector is like this. But if I am willing to take a small approximation, I can represent all the statistics that I see here with just 3 numbers. I only need 3 features, 3 final features. And if I have these 3 numbers, then I have a very good representation of the microstructure with all its statistics, complicated statistics. And now I can actually formulate my PSP models. So that's basically the story. I know I went over some of the details because they are very mathematical beyond what I just said. Happy to discuss with anybody who is interested in, but that's about it. I'm not going to do any more than that. Okay, so now examples. From now onwards, I'll just show you examples. Should be easier. So the one example that I have here, just to give you the sense and the power of the technique. This is a knowledge system that we created. In this knowledge system, you as a user can come in and put in a 3D RVE. So you can put in a 3D RVE with any morphology. So we have no restrictions on shape, size distributions, volume fractions, morphology, connectivity, connectedness or not connectedness. It's up to you. You can put in any morphology you want. Not only that, you as a user can also assign any hardening law to each of the face. So we put no restrictions on you on what hardening law you can put for the red face and what you put for the blue face. Under the hood, we have already pre-computed these models. So we already computed these models using finite element analysis on example microstructures. So we created our own microstructures. We ran the finite element models. We created these models already. So once we created these models, you as a user come in and put in your microstructure, give us the hardening laws of interest, and we instantly, as soon as you put it in, within a second, you'll get a stress strain curve. So these are some of the examples. The prediction is the blue line, is the mean prediction, because our prediction is in a statistical framework. We have a mean prediction, that's the blue line, and the red line is the uncertainty associated with it. And again, this is where things can change. Now that if I know what people are looking for, next time they come, I can actually devise this methodology such a way that I can give a better answer next time. Okay? And all of this is fully autonomous, not just automated, but fully autonomous in the sense that the computer has been shown how to create these meshes. It'll create its own. It'll create its own microstructures, creates its own finite element meshes, sends it to a finite element solver, takes the results, and automatically keeps adding data sets where it wants. And so it's continuously trying to improve itself as people ask for more things. Now that's a simple two-phase microstructure. Going forward, I can say that the same ideas, the same feature engineering, same ideas can be easily extended to 3D polycrystals. So now each voxel now actually has a crystal orientation. It's not just a phase anymore. It actually has Euler angles, 3 Euler angles to define a crystal orientation. And people generally use whole figures to see the texture, but that's what we call as one-point statistics. 2-point statistics actually captures information like grain size distribution, grain neighborhood, and all that information is in the 2-point statistics. The feature engineering is exactly the same, and then it can make predictions for effective properties, modulus and yield strength. In plots like this, these are parity plots. So one side is the ground truth, and the other side is the prediction from the fast model or surrogate model. So when you see a plot like this, the parity plot, if the model is doing a really good job, all the points should be on the diagonal, and the error is the deviation from the diagonal. Okay. And also the color schemes are always that generally what we do is gray color points are the points that are used in calibration or training the model, and the colored ones are the ones that have not been in the process. Model building process has not seen them, so they're called test points. So the idea is to show that the test points are well predicted without an overfit. Right? So the biggest thing you worry about is overfit in all these models. This is not just mechanical. You can actually take porous solids. Now the RVE now is porous, and now we are actually predicting permeability, flow. And that's complicated because flow depends on connectivity. Yet I'm still using the same endpoint correlations. They're slightly different, but essentially the same framework. The feature engineering part doesn't change a lot. And we are able to make predictions of permeability. Again, this is a parity plot. This is the mean prediction. So one dot is for one structure. So different dots are for different structures. And this is the uncertainty. So this is the mean value. This is uncertainty. And you can see they're pretty decent. You can do the same with fatigue. So now we can actually evaluate microstructures for fatigue. And in fatigue, one looks at this fatigue indicator parameters are distributions of FIPS. So as you go higher, then it's more likely to fatigue. As you go this way, it's less likely to fatigue. So these are all different microstructures. And if you are using physics-based models, you would use crystal plasticity models to compute them, and they take a long time. Each simulation takes a very, very, very long time. And these are much faster on a relative basis. They're much faster. You can see the comparison. And the ranking is about the same. Of course, there are some differences, but the ranking is roughly the same. And the fit is pretty good. You can also do with evolution, process evolution. So in this case, this is static recrystallization modeled by cellular automata. So in those models, one evaluates or looks at the evolution of microstructure. And again, these are the solid line is the prediction. The dots are the ground truth. Okay, so you can see that they're pretty close. And because we're looking at microstructures in terms of this PC scores, the predictions are showing how well the low dimensional representation of the microstructure is captured in this evolution. So it's not restricted to just static problems. You can actually do temporal problems, temporal evolution of microstructure. It's also not restricted to mesoscale. You can do the same with the atomic scale. So same thing happens. So we take atom positions, we voxelize it, then we do 2-point correlations, PCA where necessary, or some generally this more or less the same feature engineering, but maybe slightly different in the model building part. And here there's a large data set of compounds, and we are predicting the formation energy. And it does a decent job, over 1,800 different compounds. So these are now 1,800 different compounds. This is a grain boundary mobility in a single material system. The data here comes from MD simulations. In this case, the data came from a public repository. So we just downloaded the data from a repository. Here, the data comes from very expensive simulations. So I don't have as much data. And yet we can show that we can build, the feasibility of building these low dimensional models is still very much there. Everything I showed there is about homogenized properties. It turns out that another version of this or another variant of it can actually predict the local fields. So now we're not just interested in the effective properties of the microstructure, but we want to see actually the strain field or stress field, voxel by voxel. So this is ground truth from finite element. This is what is predicted by our knowledge system. And you can see that pixel to pixel, we are making incredibly accurate predictions. This is elasticity. You can do the same in plasticity. In plasticity, you worry about plastic strain rate tensor. And these are the 6 components of the plastic strain rate tensor. So we can actually do every component in every voxel for any microstructure of that material system. And we are now beginning to say any material system, but we are still working on that. So these are the big thing I want you to keep in mind before I stop that part of the talk is that these are broadly applicable knowledge systems. So we are trying to be very efficient in how we build this such a way that we don't have to go back and rebuild these models all the time, right? Because then we really haven't addressed the problem. Okay, so that's on the, now you get a sense of what we are doing and how we are capturing knowledge from physics-based models. Now, on the experimental side, we are also asking, how can we generate more data? Because most of the classical experiments that we do in material science are what I call as high quality but low quantity experiments. So in other words, we get few data points, but of course they are very high quality because you take great pains to prepare samples and we document a lot, right? So that definitely helps science, and that definitely solves a lot of science problems. But if your target is to speed up innovation, you basically want guidance so that you can rapidly screen materials, and you want to get a lot of data. You're kind of willing to accept a little bit of uncertainty or a little bit more error if you can get a lot more data at the same time. So that's a paradigm. Where is the trade-off in quality versus quantity, right? So these are all high throughput methods that we are interested in. We want to develop these methods and see how can we speed up, particularly how do we speed up materials design or materials exploration, which is a very large space because it includes chemical compositions and process histories. So every time you change the process history, it's another material, and then we want to be able to characterize and understand very fast. Not only that, not only we want to measure the macro scale properties, but we're also interested in measuring the micro scale properties. So if I have a dual phase material, I actually want to know what's happening in each phase. Why? Because that information is necessary to get some of the controlling physics. Right at the beginning, I talked about governing physics. That information of individual phases is important for controlling the physics or understanding the physics. Right? So I need techniques that will give me enough data, fast data, cost-effective techniques. So the technique that we have largely spent our time for mechanical properties is indentation. So this is indentation stress strain curve. So this is raw data. You get a load displacement curve. These are spherical indenters. So these are not sharp indenters. These are spherical indenters. The advantage of spherical indenters is there's a very small elastic portion. By looking at it, you can't tell where it is. So you need an analysis protocol. And we developed the right analysis protocol to identify this elastic portion. But it's extremely small. It's tiny. You can hardly see it. But if you identify that elastic portion right, and you apply Hertz theory, so the equations here are nothing but Hertz theory. There is absolutely nothing there other than Hertz theory. And there is just a generalization of a definition of strain. That's the only thing there it is on this side. But if you adopt these equations, these 4 equations, and you identify the elastic portion, you can convert this curve, the load displacement curve, that looks very smooth. And you can't tell by looking at this curve where there is elastic portion, where there's plastic portion. But if you actually do the analysis right, you can get a beautiful looking stress strain curve. You can see the elastic portion, you can see the plastic portion. So now you can do an offset yield strength definition. So these are indentation parameters. This is an indentation modulus. You can define the slope of this line as indentation modulus. You can define this as indentation yield strength. So you can basically do this very fast. Once you learn how to do that, you can do this very fast. So those are indentation quantities. How do you convert them to uniaxial quantities? We went through a lot of finite element simulations again, where we can prescribe the physics. So we said, if we assume that the material is isotropic and just does J2 flow theory, how do I convert? It turns out you only need 3 scaling factors. And if you apply these 3 scaling factors, you'll get a very good match between the uniaxial curve. So in both cases, the red curve is a uniaxial curve. The blue dots are from indentation, but scaled by these quantities. So once I scale this, then I can get a pretty good match. And it happens independent of hardening loss. So the material can show all kinds of different material. Again, we have done a lot in all the way from very hard and high hardening rate materials to low, soft and low hardening materials. This particular same along the same lines, but this time we wanted to know what is the error in just the estimation of the yield point, not the entire stress strain curve, but just the yield point. And we are showing that these techniques are much better, much more accurate than the current techniques that people are using to convert hardness into yield strength compared to any of them. And again, keep in mind the range, right? The range is very large, right? So again, it's from this end to that end. And we are covering a very large range of yield strengths, and we are still getting pretty good answers. Now, how do we use some of these techniques? So one of the things we have done is to look at high throughput synthesis and exploration. So this particular sample was made by Lens, and it has a gradient. It was made by Pete Collins at Iowa State University. Here he is getting a gradient, a composition gradient from titanium at one end to titanium manganese at the other end. So you get a different chemical chemistries. And then he makes bars, and then he post heat treats them. After making the bars, he is post heat treating them at 3 different temperatures. So we have are 3 bars. Okay? And then of course we can do microstructure, we can do analysis, quantification, so on and so forth, to get various measures like Cordlin distributions, volume fractions, and other things. But most importantly, we can actually get the mechanical properties just as fast, almost as fast as you can get the rest of. In fact, the samples are the same samples. We are doing the microstructure, and after we get the microstructures, then we are just indenting. So in some sense, the added cost is very little. And you can already see that some heat treatments are giving us much higher yield strengths than the other ones. So we can actually rapidly explore. But using these Gaussian models that I talked about, you can also ask about sensitivity and things like that. So you can actually see that once you start analyzing this, you can actually tell which are the more important variables. So for example, what this says is for the chord length in the beta, so the size of the beta is a lot more affected by the temperature, because that has one of the lowest values here. So the lower the value of L in the GP models, higher the sensitivity, that kind of stuff. So you can analyze and you can understand what are the sensitivities, and which then informs you as to what you should be doing next. If I'm not happy and I think I didn't cover my space well, where should I be, depending on the target I have, what other experiments should I be doing, and things like that. So that's what that helps. So that is at the bulk level or effective level, but we can also do things at the local level. So in a DP steel, we are getting properties in the martensite, which are these small indenters with the indenter radius is shown here. So the actual indentation size is really, really small, much smaller than 1 micron. So typically the difference between the indenter size and the indentation zone, the zone size is typically 1/10 of the indenter size. So you can actually compute how small these zones are. So in this particular case, we are looking at processing of these DP steels. The first set of numbers is the annealing temperature. The second set of numbers is the deformation. After annealing, you deform it by 10% in this case, a rolling reduction. And then you're doing a 170 degrees bake hardening in this particular case. So, of course, we can do as many as we want. But in this particular case, what we're showing is that the annealing temperature seems to actually, as you increase the annealing temperature, the martensite is actually getting softer, and pretty strong drop in the value of the martensite, the local strength of the martensite. But on the other hand, the ferrite is pretty much more or less constant. Nothing is happening nothing is changing in the ferrite itself, the blue. The effective value is actually increasing. Although the martensite is getting softer, the bulk value is actually increasing. That's because the volume fraction of martensite is increasing. So although martensite is getting softer, but the volume fraction is higher, so the effective value is going up. But in this deformation and bake hardening. In that process, the martensite remains more or less the same. There's no change in the martensite. But the ferrite now has gotten much stronger because of solute pinning of dislocations. And the effective value also goes up. So by being able to get this kind of information fast on complex materials, we are getting a lot of data, very useful data that can then be fed into the models, the physics-based models. That's the feedback into the physics-based models. Now, almost the last couple of slides, 1 or 2 slides left. How do I bring all these things together? This is the vision of my future lab, which we are hoping to build in the next couple of years. And in this lab, what we want to be able to do is we are constantly building this knowledge system by simulation. So we run in indentation, the physics-based modeling is all finite element. So we can run a lot of simulations. We can specify different physics, different elastic behavior, different plastic behavior. So we can specify different physics, and we can make this fully autonomous. So it can continuously keep running this and building this knowledge system, as I said before. So this is a knowledge system that's being built together based on simulations. In the experiment, when you're doing the lab, and you go into your experiment in the lab, you say, oh, I have this sample and I have all these grains I could indent, but each indentation costs me something. So I have to kind of decide which grain do I want to indent. Then the system in the lab leverages this knowledge system and is ranking the value, the information gain based on, if you do an indentation here, there is a certain information gain. So in this particular case, it's saying you're much better off doing an indentation in this grain as opposed to some of the other grains where the color is, where the information gain is very low. So in that system, then it says it does an indentation there, takes a value, goes back to saying, okay, what did I really learn from that simulation, from that measurement? Did my estimates of the elastic constants, did they really change? And if they didn't change, then where should I do the next indentation so that my ability to understand physics gets better? And so this is the loop that we have done this in a less than fully autonomous system. And it's amazing because, for example, if we are getting elastic constants, it turns out in cubic crystals, if you do 4 indentations in properly selected grains, you get pretty much the answer. After that, everything else you're doing, you're not getting a much further improvement in the estimates of the elastic constants, single crystal elastic constants from polycrystalline samples. Now, of course, the elastic constants is somewhat, everybody has those things, or they're not that interesting. The more interesting thing is if we can actually predict the CRSS values, critical resolve shear strength values, in hexagonal systems of different chemistries. And now we have different slip systems, pyramidal, basal, and all those things. So what can we do? So what we are showing you here is that by doing indentation on grains of different orientations, we are now making estimates of the elastic constants in hexagonal metals. So a lot of different metals. And also CRSS values. So this is now the CRSS values for different metals. Obviously, some distributions are reasonably narrow. That means that I'm pretty confident about some of these numbers. But some others are pretty broad. And that's the inherent limitation of this methodology, in the sense that given the samples we have, we are not able to get anything better than that. That's about what you can get from this methodology. But knowing that gives you a lot of power, because now you can decide when to engage this source and when not to engage this source. Okay? I think this is my last slide. The other technique we have been developing, and it's just very recently in the last couple of years, is the punch test. Again, people have been using punch tests forever, at least especially in the nuclear industry. So you get this load displacement curve. And then people have protocols that convert some of these to properties of interest, like yield strength, UTS, and so on and so forth. And just like the indentation methods, what we do is the other way around. We actually want to convert this to a stress strain curve. So for that, we again do the same thing. In this case, the physics-based model is still a finite element model. So we do a finite element model with a lot of different physics, plasticity physics, and we create a database, we create a knowledge system. And then when you do the actual experiment, you have the experimental curve. We are able to come back and say, yeah, based on that experiment, the tensile stress strain curve or uniaxial stress strain curve for that material looks like that. And again, the purple is the prediction, the black lines are the real experiments for a particular sample. So you can see that the same methodology works even for SPT. So with that, I think I'm going to stop here and take questions. The message, the take home messages are that data science and machine learning has made tremendous progress where it is actually ready for domain scientists in materials and manufacturing to be able to take advantage of what they offer. But the way you apply them has to be very carefully thought through. Usually a brute force application of machine learning tools will not give you the kind of results I'm showing you. So, but if you properly apply them, you can get insights that you would otherwise not get. The second take-home message is we do need to make or develop high throughput assays or synthesis and evaluation protocols so that we can generate a larger amounts of data so that we can make smart decisions, especially if you want to accelerate materials innovation. If you want to bring the materials innovation cycles in line with other design cycles, you do have to adapt, design, develop, and adopt high throughput methods. So with that, I'm going to stop, take questions. Hopefully it made sense. It made some sense.
Thank you so much, sir, for a memorable lecture, giving us an overview of emerging paradigms in materials innovation, depicting the core knowledge needed to support accelerated materials innovation, explaining ways for addressing challenges related to accelerated materials discovery and development, the central focus of the materials genome initiative, importance of data analytics and machine learning tools, and multi-resolution high-throughput mechanical testing. Thank you once again, sir. May I request Dr. A. Urupine, Vice Chairman, IAM Chennai Chapter, to conduct question session.
Yeah, thank you, Pani Madam. Surya, it's a very enlightening lecture. Thank you for giving such wonderful lecture. Then we'll start with my first question. Myself, being a moderator, I have a privilege. So in the multi-resolution, the measurements you carried out, the role of interface, how do you capture that to the physics-based model? Because in DLFST, the interface boundaries are important in terms of predicting the properties, getting the generating mobile dislocation, for example. If you're doing a highly localized measurement, the interface information is missing, I suppose, right? And how do you capture that?
So this particular one, we didn't do this, but in a simpler material, in a single phase material, I think it was aluminum alloys, we did studies where we systematically approached the interface. So we are doing indentation as a function of the distance from the interface. So in that sense, we are indirectly interrogating what is the role of the interface, because when you go far away from the interface and you do an indentation, a very local indentation here, it doesn't even know there is an interface. But as you systematically come closer, you can start seeing the differences. And by studying the differences, and again, almost all the methods, one part you have to focus on is what data are you collecting, and you have to be very clever in how you design your experiments. There's no way around it. But to make sense of the measurements that you have, you need a model. Without a model, it's very difficult to make sense of any of these models, any of these measurements, right?
Yeah.
So in order to make sense of that, the effect of the interface, then you need a suitable interface model. But if you have an interface model and I have these measurements, now I can say something about the interface.
Yeah. Got
Makes sense?
Good.
Right?
Yeah.
Does it make sense?
Yes, exactly. Okay, thank you. So I see Dr. Bakshi.
Yeah. So, it's a very nice lecture. Nice to see the extent to which we can use these techniques, in predicting things. And I've been thinking of learning machine learning for some time. So this is a good start for me. I wanted to know if you had used voxels to quantify a microstructure. How does the size of this voxel, affect the, the parameter that you get to quantify? So how do you decide that?
Yeah. So excellent question. Right? These are all very important questions. So because I'm using PCA, so the techniques I'm using, you have to standardize voxel size. So if you mix up voxels of different sizes in one study, then basically you're mixing apples and oranges, right? You don't get anything useful. So you do have to standardize. And the question about how do you standardize is really that there are, because I'm using FFT algorithms, uh, the the signal processing people have already told us that the smallest feature should have at least two voxels in each direction. That's a minimum. The smallest feature, right? It's a lower end estimate. He's saying that voxels cannot be large, that you have only one voxel in one of the feature, one of the regions. It has to have two in each direction. So in 3D, you should have basically two in all directions. So that means that you should have at least eight in 3D, right? So that's the minimum side. And the maximum side, of course, I mean, you can, of course, have much smaller or many more voxels, but then the computational cost goes up, right? So there you're going to make a trade-off saying that I cannot afford more than this many voxels. And to standardize the voxels, there are a whole lot of signal filtering techniques. So if you happen to use one voxel size for one study, and then you have to change it to the next one, so you're basically remapping the microstructure. There are a lot of filtering techniques that can, a lot of signal processing tools that will let you remap depending on what your needs are. I hope that answered your question.
So sometime back, I had attempted, quantifying the effect of carbon nanotube distribution in the microstructure on the mechanical properties, and try to actually quantify the microstructure in very basic terms, and correlate the nano indentation data, variation in the nano indentation data, to the variation in the volume fraction in each zone, let's say throughout the microstructure. So that's where that would be very interesting to see how we can apply this more advanced knowledge to that kind of nano composite.
So in these plots, I forgot to say this, but it's there in the papers. Center voxel is always volume. I mean, especially in these kinds of representations. Now, it's not true for all of them. In this kind of representation, the center voxel is always volume fraction. So one of the features is always volume fraction. So the volume fraction information is there within the representation, right? But it has more than that. So the rest of the statistics are telling me something about the shape and size and location and all those things.
Yeah.
But I agree with you. I think it'd be useful to look at these tools to see whether or not they offer any value.
Thanks, Dr. Bakshi. And I see a question from Dr. Satyesh Yadav from IIT Madras. So his question is, do we expect to have a lab where robots would make alloys and optimize the process parameters with the help of machine learning to get desired properties in future?
Yeah, no, we want not expect to. We are already building one, right?
Yes.
we are in the process of building one. So that's what I meant by saying these are not too far away. So we are actually, it may not work, right? I mean, the entire thing is that I don't know whether it will work or not, but we feel strong enough that we feel like we should build one, and we have funding for it, so we are going to build one. So we'll see what happens.
Yeah, great. Good answer. Dr. Satyas, is that answer your question? I think I see your in the line.
Yes, sir. Yes, sir. Yes, that was Professor Surya, thanks a lot for this excellent lecture. So yes, I keep hearing, especially people who are working on chemistries where there are few chemicals to handle.
Right.
So robots are already into action. So similar ideas you are probably pursuing for LOIs.
Yeah, you said it exactly right. So, and also there are these other guys, right? Like Benji at AFRL has this system, RS system, ARES thing, where he is looking for nanotubes, right? He's trying to improve the quality and quantity, I mean, the production rate of nanotubes. So some of the other things are there, but people, I think in the structural alloys, it's just beginning. And I think some of the things that I presented to you are at the edge, at the forefront of that. So again, there are other ideas too. I mean, so who knows which will eventually work and which one will fall apart? Who knows, right?
Okay, thank you, sir.
Yeah.
But we are very hopeful, though.
Yeah, it's good to hear, Professor Surya. And so maybe one question from YouTube comment we can take. Yeah. So from Mr. Hariharan DS, his question was, is it possible to get back the microstructure from endpoint statistical parameters, the 3 parameter which you have shown?
Yeah. So it's a good question. So I think there are 2 different things. This is a PCA representation. This is the 2-point representation. So here there are more than 3 parameters. In fact, the number of values here for this particular example, it turns out the number of voxels in the 2-point map is exactly same as the number of voxels here. So the number of unknowns, the number of parameters between this representation and this representation is exactly the same. Turns out for something like this, you can actually recover even from 2-point statistics. You don't even need endpoint statistics. Even from 2-point statistics, for something like this, you can recover exactly 1-to-1. But that's not a general statement, though. There are some places where things fall apart, and there you need some more information. But of course, when you go from here, from this representation to here, you give up a lot more information. So there it becomes harder to get everything back. But you'll get something that looks similar, right? Because the only thing you give up are the differences in the statistics from here to here, right? So every point in this map is a statistic, and the difference between this and this is the statistics. So you are representing the statistical map using this, and the difference is gone. If once you adopt this, that difference is gone forever. There's no way to recover that. Make sense? Or
yeah, okay, yeah. I hope Mr. Hariharan, now you got the answer for your question. So maybe one more question, we'll take it within the time. We have 5 more minutes to wind up. From Mr. Sujit Kumar. Professor, you are using 2 different intended geometry for analysis, 1 micron and 16 micron. Does the size of the intended tip has any influence on the measure property?
Okay, so that also is a good question, very good question. So there's a lot of literature on what is called as indentation size effect, ISE, and that is a very different thing. They're not talking about different indenters tip sizes. They're talking about when they punch in, or when they do an indentation with depth, with increasing depth, they find a different value of hardness. So that's a very different phenomenon. So it's not the same thing that I'm talking about. But in our case, for the examples that we looked at, the size of the indenter, when you go to very, very, very small sizes, then, for example, you get what are called as pop-ins. In the sense that when you go to very small sizes, you're not able to establish a Frank Reed source. So you cannot get the smooth transition from elastic to plastic. It builds up until the zone size is big enough that it can pop, it can actually release a Frank Reed source. And then suddenly you get a lot of plastic deformation. So there's a burst of plastic deformation. So there are size effects of that kind, but there are no size effects where, because I use a different indenter of different size, I'm getting a different yield strength itself. So in our techniques, we haven't seen an effect of, for example, if you take a single crystal material and you do indentations with different indenter sizes, because it's single crystal, you should expect to get the same yield strength, and we get the same yield strength, except when you go to very small sizes and then you get these pop-ins. and there you have to extrapolate, back extrapolate. So then you don't know whether you're getting it, depending on the pop-in. Sometimes it's very hard to extrapolate because the jump is very large, right? Hopefully that made sense. So, go ahead. So the values that I'm reporting here, we assume we treat them as if they are not material length scale dependent. So they're intrinsic properties of the material. That's what we argue.
Murugan, you are muted, probably trying to talk. I think you are muted.
Yeah, okay. So I see not many questions in YouTube comment. So with that, maybe we can wind up. The time is also up. Rani Madam, so back to you. So thanks.
Thank you, Dr. A. Murugan and Dr. Surya R. Kalidi. Now it's my pleasant duty to request Dr. Shajik to announce PRML award to Dr. Surya R. Kalidi.
I can stop sharing, I guess. Okay.
So we have a great pleasure to award Dr. Placid Rodriguez Memorial Lecture instituted by Indian Institute of Metals, Kalpakkam and Chennai for the year of 2020 to awarded to Professor Dr. Surya R. Kade Hindi, Regional Professor, and Ray S. Frank H. Neely Chair, Professor, Interim Director, Novalis Innovation Hub, Georgia Institute of Technology, Atlanta, USA. For the talk, and the talk revealed accelerated materials innovation using knowledge system and high throughput experiments. Thank you.
Thank you, sir. Coming to the end.
Thank you. Thank you very much. Thank you.
Coming to the end of the program for today, I request Dr. Rani P. Judge, convener PRML 2020, head SMCA CSTD ICCR Kalpakkam to propose the vote of
respected dignitaries, members of IIM chapters, IGCAR and IIT Madras, and all the participants of the online program of PRML 2020. On behalf of the Placid Rodriguez Memorial Lecture Organizing Committee, Indian Institute of Metals, Kalpakkam and Chennai chapters, it is my proud privilege to state the vote of thanks. Our deep sense of appreciation and sincere thanks to the 12th Placid Rodriguez Memorial Speaker, Dr. Surya Kalidindi, Regents Professor and Reyes Francis Neely Chair Professor, Interim Director, Novalis Innovation Hub, Georgia Institute of Technology, Atlanta, USA, for accepting and delivering an excellent PRML 2020 lecture on accelerated materials innovation using knowledge systems and high throughput experiments. Thank you so much, sir. Now, let us say heartfelt thanks to Dr. V. Jagadish Kumar, Dean, Academic Courses, IIT Madras, for readily agreeing to be the chief guest and deliver an interesting address, and also for all the support for conducting PRML 2020 online mode from IIT Madras. Though he is part of PRML family, let us express our hearty thanks to our PRML chairman, Dr. Shaju K. Albert, for his interesting address, guidance and support for arranging this program. I'm so happy Madam Blossom Rodriguez is able to participate online this year. Thank you so much, Madam. Your presence always motivates us. I'm very thankful to Dr. A.K. Baduri, Director IGCAR, for his continuing support for the program. I should thank esteemed members of IIM, President IIM Ivan Kokle, past President of IIM Dr. U. Kamachi Mudri, all the past presidents, all IIM Council members, members of all chapters, head office who have participated and also send us best wishes for this program. I will place on record my thanks to Dr. Kamaraj, PRML member, Dr. T. Sundararajan, Chairman, IIM Chennai Chapter, Dr. Murugayan, Vice Chairman, IIM Chennai Chapter, Executive Committee of IIM Chennai chapter for perfect support and guidance extended to us for making this online program a big success. Now I thank Sri Jagadishan, Head Computer Division, Rajan, Mr. Baby, Mr. Shivashankar for all the support and streaming facilities in IGCAR and also SIRD for Wi-Fi facilities. And I should not forget my chairman, IIM Kalpakkam chapter, Dr. Divakar, Secretary Dr. Karthik and other executive committee members who supported this program. I thank Ms. Paneer Selvi for comparing the program nicely. I thank Ramesh VRK Printer for the e-booklet. And last but not least, I thank each one of you. Your participation has only made this program a huge success. Thank you.
On behalf of organizing committee, George, convener PRML 2020. Thank you all for being here today. Thank you.
Thank you, Kamraj. Thank you.
Thank you, sir. Thank you, Professor Surya.
Oh, thank you very much, guys. Sorry about that call. I don't know who it is, but I tried to cut it off, but I